正在录制此会议。
Okay, so let's consider the capacitance as we previously mentioned. If you are working with the external voltage at the different regions, we get different capacitance because the charge accumulation. So we've discussed the capacitance voltage relationship under different biasing. The charge and the capacitance for MIC is voltage dependent. As mentioned, we have the varied resistor. And the voltage-dependent semiconductor capacitance can be first determined by how much charge accumulating within the structure divided by the voltage caused around the external capacitor. And this relationship is determined by the different biasing condition. So you can see the slope may slightly vary in between the system. So you can go back to the previous slide discussing this charge accumulation versus the voltage applied. So if you want to look ahead, what is the corresponding accumulations of the charge? We take the slope of this capacitance. So you first talk about the simple case in which we get a strong accumulation. So for strong accumulations, we get the charge with the same type of semiconductor accumulating along the semiconductor surface. And under that constant, we get the same capacitance, almost the same with different voltage. What does this mean? It means that your dielectric work as a simple capacitance, just like in the accumulation condition. We can operate or change the charge here and here for the accumulation region. So under this the constants, we this one, so we get an accumulation region. We get the same type of charge accumulate here, and the opposite type of charge will accumulate along the metal surface. So under the constant, you get a simple dielectric capacitor. Okay, so the simple dielectric capacitor will be the capacitance will be the same of epsilon s multiplied with the area over the distance of the insulator. So it gives you a constant of the capacitance. However, when you try to deplete or you first consider the flat band condition, so when you consider the flat band condition, we start from here. So we get a weak accumulation. The accumulation is only determined by the doping concentration. So there is no enough charge to be modified. So you can see that under flat band condition, we get slightly low capacitance in comparing with the strong accumulation. And furthermore, if you consider depletion region with the voltage on the other side, so you can think that there is a flat band voltage in between 0 and the flat band voltage. The reason is because we get a metal, the work function between metal and the semiconductor. So since there's a difference, we need to use the flat band voltage. Maybe you consider if the flat band voltage is negative. That means in consider the flat band in which we have a phi m, which is less than phi s. So we add additional negative voltage in order to get the flat band condition. So at the flat band conditions, you can see the charge is we do not have that much charge accumulated. It's only determined by the doping concentration. And then so we try to use the deplete regions. So you applied a certain voltage to deplete the majority carrier. When you deplete the majority carrier, you get a least charge accumulation. Okay, so since we get least charge along the semiconductor surface, that gives you least capacitance in comparing with the strong accumulation. However, later on, if you still work with the low frequency, what does this mean? If the frequency is just a few hertz or less than 1 kilohertz, the modulations will be considered like we get additional accumulation with the inverse layer. Once we get a strong inversion layer, so we go back to the previous capacitance. So if you look at the inversion layer, we get the charge accumulation along the surface for p-type semiconductor with the electron accumulating along the surface, just like the inverse charge. And then we get a positive charge along the surface, just like the thing here. So it works again like a capacitor separated by insulator or oxide, and the capacitance will be proportional to epsilon A over D. Okay. So under this the constant, you go back to the original capacitance our value. So it will go down because we do not have any charge along around the depletion region, and the data go up for both inversion layer and also stronger accumulation. But if you look at some interesting case, is that you get two different charge accumulation or capacity. There will be a combination. So if you go back to the previous slide, what is the combination of these two cases? You get the charge accumulation here, but you still have some charge along here because we get a positive charge for p-type system, but later on we have accumulation of n-type charge electron. So there will be certain charge accumulations and displacements or relocation within the semiconductor region. So if you consider capacitance, it's just like a cascade connection with two capacitors. So by considering these two cascade connection, if you get the capacitance in serial, what does this mean? It means that you need to take like a resistance in parallel. So you get the total contribution to the capacitance equals to Ci CD over Ci plus CD. So you can think the inverse of the total capacitance equals to 1 over Ci plus 1 over CD. So Ci indicates the insulator or gate oxide capacitance between the insulator. So which is just like epsilon S over D. And for CS, it is the voltage-dependent semiconductor capacitance. So depending on how much charge distribution along the semiconductor, we get the CS or CD. Okay. So under this constant, the CD will only matters if you consider the depletion region. So we typically mentions this CS as CD. If you are working with the stronger accumulation, typically there is no additional charge distribution because if you are working with accumulation, there's only hole accumulation. That means you get a positive charge along semiconductor and a negative charge along metal. So it just works at the same time. But if you work with the inverse or depletion regions, we get the change of charge from hole to electron. So under that constant, you also get the distribution of the electron, in which it is related to the dielectric constant in semiconductor and also the depletion distance over the W. And then so we can judge this value based on CS or CD. And then maybe you will be pretty confused why we label a C medians at high frequency. So imagine that if you are working with really weak inversion or strong inversion layer, where is the meiotic carrier? Where is the electron? So I already mentioned earlier that this meiotic carrier is drawn from some free generation carriers that's Ni from the bulk material. So you can consider that even we assume it is strong inversion, we try to accumulate the electron, but where is the electron? It's from here. And what is the percentage of this free electron? It is really low because if you have a tight doping of p-type semiconductor, it could be 10 to 17. So you take the n square or ni square divided by Na, you get the free electron typically on the order of 10 to 3. So you want to accumulate the electron from here, from accumulating the bulk from accumulating the electron from the bulk material. So it will be a long distance and really far away, time-consuming accumulation process. However, if you change your voltage really fast and you want to change the potential and change the electron, if this frequency is high, maybe several megahertz, it is hard to modulate your channel because you need to wait for the electron moving from the back material to the surface. So there's the time dependency. Okay, so if you modulate it really small, what happens here is that these capacitance will be determined by the semiconductor capacitance. So you get the capacitance induced by depletion QD Okay, so you can consider that the depletion area or the 2D. We previously said that in BJT we modulate the minority carrier between the base region. So we modulate the carrier, which is the shaded area in BJT. And here, as you can consider, we try to modulate the charge here. Okay, so these modulations of the depletion charge will be proportional to QNA Qmax. So you can see we try to modulate the doping or the depletion charge. When you modulate this depletion charge at the depletion region, um, what happened here is that since we have two contributions, the first contribution is the charge along accumulation along the surface using the strong inversion. But since we don't, the carrier is not fast enough. So the minority carrier, the electron, may not catch up the frequency. So you do not have the capability to move the electron from back to surface. That means you do not have any insulator capacitance or the gate oxide capacitance. So even we can do accumulation at the DC without frequency modulation. But if you do some voltage modulation, even we still have accumulation, but this accumulation seems to be a constant. So there will be no capacitance change. Okay, so under this the constant, the capacitance should be still low because we do not have carrier modulation. But where is the carrier modulation? This carrier modulation is then determined by the cascade connection of this capacitor in depletion region. So you get the depletion region of the charge, which is determined by this function. So the depletion charge is determined by how much charge you modulate in the depleted area here. Okay, so we try to deplete the areas. We try to change the majority carrier because majority carrier is doped entirely within the buck system. When you apply the voltage, it will shift this curve up and down. That means you can modulate the whole within the depletion region, but not the free carrier along the surface. So the modulator areas, or you can only modulate the carriers along the depletion region here. So what happened is that the capacitance is in semiconductor, or we call it CD. Okay, so the capacitance in depletion region, if you get the width, which is much larger, you get a small capacitance, and you get the capacitance in serial. That means after connecting with a small capacitance, you are determines the total capacitance is determined by the small capacitance. So at high frequency, the capacitance is low. Okay, you do not have any modulated modulated carrier along the surface. You get a modulated carrier along the depletion region here. Okay, because we can only modulate the majority carrier at high frequency. So in comparing with the low and high frequency, it will strongly change the behavior of your frequency response. So you get the capacitance at high and low frequency. In high frequency, you only have the minimum frequency by connecting with the depletion region. But for stronger accumulation, since this modulation is mostly modulated the whole concentration, so the speed can be fast. And then in stronger inversion, if your frequency is low, we can still modulate the electron along the surface. But if the frequency is high, you can only modulate the majority carrier as the deplete junction, as the deplete capacitor, and the electron cannot be modulated along the surface. So here is the summaries in which we have the previous slide. In accumulation, the slope of these modulations is steep, in which we have a large CS. So you can go back to the previous one. Accumulations of this charge is high. We get a steep slope of the whole accumulation. That means you take the dQs over dB, we get a large capacitance, just like a constant here. But other times, if you consider the depletion region, you need to consider the deplete of the majority carrier in semiconductor. For P-type semiconductor, it is whole. So when you modulate the whole concentration in p-type semiconductor, we get CI/CD, which is in serial, and this is the combinations of the CD depletion layer capacitance with the insulator capacitance defined by RSI insulator. And then we can consider what is the width of the depleted layer. So if you consider the width of the depleted layer, it should be proportional to the square root of phi f. Okay. So once you increase the width, it will decrease your capacitance, because you have a large width, you get this capacitance. So you can see here's the dependency on the square root of phi s. Okay, so the slope will increase, the charge will increase by the square root of phi s, but the depleted capacitance will decrease by over 1 over square root of phi s. And also, we define started voltage, larger the threshold voltage. This threshold voltage is defined by the insulated voltage plus 2 phi s. Okay, the inversion layer in semiconductor and the total voltage across the dielectric layer. The small signal capacitance determined by the measurement of frequency. So there will be high frequency range in which we need to consider both the CD and the CI. If you are working with low frequency, we only have the strong inversion in this one. But maybe you question why in low frequency we still have the connection of CI and the CD, but we have a high capacitance. Okay, so the reason is because when you have a strong inversion layer around here, so you can see the capacitance is connected both from the CI and the CD. If you have a high capacitance, the capacitance in series determines by this high capacitance. So as long as we have the multi-carrier modulated along the surface at low frequency, we can have the equivalent capacitance, which is at high capacitance. Okay, and now how high it is? So the frequency is around 1 megahertz, in which we can seldom move the multi-carrier from the back materials to the surface. In the inversion layer, cannot change immediately. So it cannot contribute to the small signal capacitance. That means you modulate the signal slightly, but you cannot form the charge distribution. You cannot change the charge distribution. So it is determined only by the deplete in the semiconductor region. So the insulator, it doesn't really matter, because along the insulator, we do not have additional minority carrier of electron accumulating along the surface. So we only modulate the depletion carrier. At a low frequency, maybe 1 to 100 hertz is really low, so we can move the minority carrier in the back material and drift across the depletion region to the inversion layer. So we can wait until this charge accumulate, and then later, once it accumulates, we can get it large capacitance determined by CI again. So we get a smaller distance between the dielectric oxide. We get the typically distance maybe micrometer scale. So if you get a smaller D, you get a large capacitance. So that's the reasons we get a better resistance than CD, which is determined by the larger depletion region. And also, do we get a high capacitance in accumulation? Because in accumulation, we modulate the majority carrier instead of minority carrier. For majority carrier in p-type region, it is whole. So we can modulate the whole really fast in just a megahertz range. But if you consider the majority carriers, the recombination rate will be several hundred microsecond. That means you need to operate the frequency less than 1 kilohertz. Okay. And of course, there will be some non-ideal case. What does this mean? There will be some work function difference between the doped silicon gate, and also there will be some doping and defect along the surface. So for instance, if you thermal cores the oxide, maybe you get a certain defect along the oxide surface, or if you get a certain doped materials along the metal plate, you get a certain defect or some trapped iron along the surface. So that will change your surface energy and also change your surface potential. And also you get available charge along the silicon oxide interface because you get some lattice mismatch, so you get a certain defect along there. So considers the work function difference. We previously say if your metal work function is different with the semiconductor work function, you need to use the flat band voltage to flatten the intrinsic layer and the band in vacuum level. So for instance, if your work function in semiconductor is larger than phi m, this VFB will be negative in order to apply additional positive voltage along semiconductors than metal. And the reason is the constant, you can compare data for both N-type N plus poly P silicon or N plus poly N-type silicon. You can see what is the corresponding Fermi level needed. So we consider that if you P-type system, we get a negative phi ms, in which do we get a phi s which is larger than phi n. So this phi ms is determined by how much doping. So if you get a higher doping, you can tune the Fermi level. If you get the N plus doping, that means you get the more. So we consider the acceptor. So here's the donor and the acceptor. So if you consider the N-type regions, you get more donor. If you get a A-type P-type regions, you get a more acceptor. So you can shift your Fermi level. So you can consider if you get a if you go back to the previous slide, talking about the flat band voltage. If you get a more P-type region, it moves the Fermi level down along the valence band. That means you need extra band bending construction, flat band voltage, more negative voltage in order to get the flat band condition. And the vice versa, if you working with the N-type region, you have the Fermi level above the intrinsic layer. So if you get is higher, it means you get the least negative voltage to apply for phi ms. So that explains why we have this positive and negative trend for both N-type and P-type condition. So you can consider that by changing the doping, how do we shift the Fermi level? And as long as the phi ms is less than 0, that means you need to get a negative voltages to get a flat voltage for phi s larger than phi n. Okay. And then here's the interface charge as we previously mentioned. If you get the interface charge along the state, along the service, typically this will have a several contribution. The mobile ionic charge, so typically introduce positive charge along the oxide and the sodium along the oxide interface. So we get sodium ions, and therefore it will induce additional negative charge in semiconductor. So depending on how do you dope or how do you coat the metal, if you get this kind of trapped positive charge in oxide, we get the oxide along the surface of the metal and oxide, so you get the positive charge. It will introduce additional negative charge along the semiconductor. So that means you get a more band along the semiconductor surface. And also, do we get certain oxide trapping charge in between the oxide layer, in which it is induced by the imperfection in the silicon oxide layer? And also, do we get the interface charge along silicon to silicon oxide layers? It will induce additional interface charge. And this one something when I work at the industry, typically how do we change it and how do we avoid it? It will be pretty important to clean the semiconductor surface, clean the channel, and change the temperature and change the annealing temperature in order to minimize the interface charge. And also, do we get some oxide fixed charge induced by the transition layer between the oxide semiconductor? So you can consider here's we get silicon, here's we get silicon oxide. When you do silicon oxide, it is not an abrupt layer. You need to transfer it slightly. So slightly increase the oxide concentration to x to 2. So there will be some transition fixed charge induced by the semiconductor oxide transition. So this is also pretty important in order to deal with the charge. So all of these things will impact what is the corresponding Q phi m, the work function phi ms. Okay, so if you have different phi ms, what will happen? you will get a different flat band voltage, and then also you get a different threshold voltage, because threshold voltage indicating how much total voltage across the insulator and the semiconductor. So when you have different threshold, you didn't know how to turn on the channel. But that will be a cool thing if you can adjust the threshold a little bit. So like in metal gate in process like Intel and the TSMC, what we have is that we have different metal layers. So for instance, we have titanium oxide, we have a hafnium oxide. So by changing the metal work function, we can slightly adjust what is the threshold voltage, even with the same oxide and the semiconductor. And of course, you can get a different doping, but we seldom change the doping to meet the condition of different threshold voltage, because we see the products like in N3 or N5, typically we have 6 to 8 different threshold voltage, like ultra low voltage, standard voltage, in order to satisfy with different device. So when you design with different, like we want to design high power, we typically use the SVT, like the standard cell. But if you want to work with really low leaky current or low operation voltage, we change the metal combining condition. So instead of using different doping, we change the metal connection, and try to avoid any unwanted defect like the interface trap and the oxide trap. So maybe you have different metal connection, metal composition along the metal gate. So Intel and the TSMC, they try to use different metal composition. That is also like a really trade secret if you want to generate a single doping semiconductor with maybe 6 to 8 different threshold voltage. And also we have some effective parts existing along the service, and also we have an interface charge for different facet or different crystal structure. So for instance, if you work with silicon, you have two choices. The first one is uh, 100, or you can use 111. But why we only use like 001 as the service for silicon substrate? The reason is because the interface charge is typically 10 times higher, or you can say unwanted charge is 10 times higher for 111. So we seldom use this one. On this, you are going like a silicon carbide, or you are working with hand structure like a gallium nitride, who wants to grow a pure defect-free 3,5 material, some 111. You can use this one, but we seldom work this one because the service charge is typically high for this semiconductor. And if you have this service charge, as we mentioned, it will even we get the same like a 5S and a 5N, but you get a certain banding, like we get the service charge, positive charge here. We can have certain negative charge along the service. So you need to consider additional charge, entrapped charge along the surface. So previously, if you do not have any interface charge, you will get a flat band voltage equals to the difference between metal and the semiconductor work function. And here we assume the work function between phi n and phi s are the same. But since we get a service charge, we accumulate additional negative charge here. So you can see there will be some Fermi level, which is slightly higher than EI. So when we meet these conditions, we want to precisely operate your MI or MO systems, we need to still apply the flat band condition. So even with the same phi S and phi N, due to the service charge, we need to additionally give it a flat band condition. So initially we have the electric field from left to right. So in order to compensate this charge, we get additional negative charge from semiconductor to metal. So we compensate the initial trap charge. Okay, so if you want to look ahead for the flat band condition, you need to consider both the trapped charge and also considers the initial work function between semiconductor and the metal. Okay, so these things you can consider what is the contribution to the threshold. So we consider the flat band voltage, including the metals to semiconductor work function difference, and also the trapped charge in interface charge. And at that time, we consider the depleted charge along the depleted region, the semiconductor region, and plus the two phi F. So you can consider the first two part is the flat band condition, and the second two part it is the threshold voltage as we previously mentioned. So we get the threshold deplete voltage plus the 2 phi F. Okay. So when you have these conditions, you can justify in any kind of MI's construction how large it is for the threshold voltage. So the interface charge is positive, you get an additional minus QI10, which is negative charge. So if you get a positive charge in the interface, you get additional negative terms in the threshold voltage. So you can compare that how much threshold we need to apply. So if you get the phi n larger phi s, in which we get a positive phi ms over the flat fan voltage, you can compare it with the previous one. If phi s is larger than phi n, the flat band voltage should be negative. So you get the phi s larger than phi n with a negative flat band voltage. And similarly, you get the flat band voltage. As we previously mentioned, the QI is positive. Okay, so we get a QI positive, need a flat band voltage with the electric field from semiconductor to metal. So once you get it flat, we can consider what is the deplete type and what is the accumulate surface potential. And as we mentioned, if you get a positive surface potential, that means you apply the voltage on metal side. You get an N-type channel because we get the electric field from metal to semiconductor. So under that schemes, it will work as an N-type condition. And also for depletion region, it should be deplete the P-type region. So if it should always be the same biosic condition. We want to deplete the positive charge and we want to accumulate the negative electron. And also, if you want to work with P-type channel in N-type semiconductor, for P-type channel, we have the surface accumulating with hole. So under that constant, we need to apply the negative charge along the threshold. So we get the metals with negative charge. So that will give you hole accumulations along the semiconductor process. Okay, so by combining all of these things, we can determine what is the corresponding threshold for MI's condition. Okay, so that is really important when we determine the channel for our later on for the MOSFET. And for the capacitance relations, we already talked about that the interface, the capacitance is connection between the semiconductor and the insulator. If you have the interface state, we already add additional interface charge as the flat band voltage. But we can consider this one if you have this interface. How does it works like? So we get additional interface charge. That means maybe if you apply the voltage, you can modulate it. So there will be additional capacitance in parallel with the semiconductor capacitance. So the semiconductor capacitance can be expressed by epsilon S over W, which is the depletion region. We get additional CIT. So this one will get a difference in between the ideal case and the real case. So you can see that the practical case, if you consider the low frequency response, we can see the interface charge is typically low frequency response. So you get a high frequency, you can get rid of this. But if you get the low frequency response, you can see previously we assume it will go down and then go up abruptly. But there will be a slight increasement because you have the capacitor in parallel. There will be the summation of two capacitance. So you add this interface together with the semiconductor in depletion condition. So you add it together, so you slightly increase the capacitance in the total effect. So that is how it looks like. So if you get the interface chart, you will get a different capacitance, you get a different threshold voltage, and you get a different summation total effect of the capacitance. It should be I think the last style I want to mention here is that if you have interface state, you get a different threshold. So you get this capacitance by adding additional depletion region instead of single layer. This is because the change of the charge in the semiconductor, you can see the defect is will be permanent. So you can see this unoccupied interface state. Initially, you only see here, but when you have the inverse one, you get more interface state as the summation of the change in depletion charge. So they are equal in magnitude, but unsaid. You can see if you get a strong inversions, you get an additional occupied state. So the depletion state will have a factor of 2 in front of it at the threshold voltage because we try to build up the minority carrier along the surface to form the channel, N-type channel. Okay. And then also, so when the fire is extended by voltage, the trap is below the Fermi level, and it results in the capacitance. So previously, we saw the change it in accumulation type. You typically will not see this defect, but later on, so when you are working with accumulation type, like we get these turns further down, we get more trapped charge or trapped position to form additional capacitance. Like we have the carrier modulation here, and we have the defect modulation below the Fermi level, below the above the Fermi level. So you can see the Fermi levels will give you certain occupation and forms the capacitance. So this is some unwanted factor. I don't want to talk in detail further, but you can think that we need to consider. I think the threshold power is the most important part, and what is the total effect for the capacitance. And I will maybe not talk more about the imperfection interface state and also how it changed the capacitance. So in the meantime, I believe this it will be a must-have question. So how, if we get a certain interface charge, if we get a certain difference between work function, metal work function and the semiconductor work function, and if you want to tune it in strong inversion, how does the threshold looks like? And do you know what is the corresponding relationship if you have different doping, how it change the fed band voltage, and how does the fed band voltage change within the carrier, and also how much capacitance we can build up at high frequency and low frequency. That is the important part for this chapter. Okay, and thank you very much for joining, and hope you enjoyed the online course, and let me know if you have any suggestions. Thank you very much.